Imagine yourself standing on the surface of Mercury, but not the Mercury you usually picture, not the scorched, sun-blasted daytime inferno. Instead, you're here, during the planet's incredibly long night. The sun set weeks ago, and it won't rise for weeks more. Above you, the stars are stark and brilliant against a perfect black, untouched by atmosphere haze. The ground beneath your heavily insulated boots is rigid, radiating away the day's heat into the vacuum of space. It's a silent, desolate landscape. But tonight, you've brought special equipment, not just for survival, but for observation. You point a sensitive detector tuned to a specific wavelength of light towards the anti-solar point in the sky, the direction directly opposite where the sun lurks below the horizon. And you see it. Something faint, ethereal, almost unbelievable. Stretching away from the planet, reaching impossibly far into the blackness, is a ghostly, elongated glow. It's a whisper of light invisible to the unaided human eye. A delicate structure, millions of kilometers long, trailing behind this tiny battered world, like the train of a spectral gown. Mercury, the seemingly inert little rock closest to the sun, is doing something deeply strange in the dark. It's venting a tail into space. A tail made not of gas or dust in the way we usually think of comet tails, but of something far more specific and intriguing: sodium atoms. Join me today as we delve into one of the solar system's more subtle and surprising phenomena: the vast, invisible sodium tail of Mercury. We'll explore how this bizarre feature was discovered, investigate the complex processes that create and shape it, and understand what this ghostly appendage tells us about the innermost planet and its relationship with the Sun. When we think of planets with distinct features, Mercury rarely comes to mind. It's the runt of our planetary family, a tiny cratered world baking in the sun. But in 2001, everything changed. Scientists have been using specialized sodium filters to observe Mercury since the mid-1980s, when it was found in the planet's exosphere. That's exactly what the team at McDonald Observatory in Texas were doing when they spotted something strange. A faint glow extending far beyond Mercury's tiny disk. Initially, they didn't believe their own eyes. They thought it must be the result of an equipment malfunction or data processing errors. But after thoroughly checking and double-checking, the astonishing truth emerged. Mercury was trailing an enormous structure through space, a tail of sodium stretching almost 2.5 million kilometers behind it. For perspective, that's 700 times the width of Mercury itself. The discovery was humbling. Mercury isn't some distant, obscure object. It's one of our closest cosmic neighbors. We've been observing it since ancient times, and even visited it in the 1970s and the 2000s, thanks to NASA's Mariner 10 and Messenger spacecraft. And yet, this colossal feature remained completely undetected until the 21st century. The discovery was a big deal because it challenged our classification of what can have a tail in our solar system. Suddenly, Mercury wasn't just a bland, cratered world, but a planet with a dynamic feature rivaling the most spectacular comets. So, how is Mercury's tail different from comet tails? And why would this planet have a sodium tail specifically? The answer is the fascinating result of Mercury's unique position, composition, and the Sun's fierce influence. Comets are kind of like snowballs hurtling through space. They are mainly made of ice, which sublimates as the comet approaches the sun, leaving behind a trail of ionized gas and dust particles. In contrast, Mercury is a rocky planet with minimal, if any, ice. Scientists think there may be ice hidden in permanently shadowed craters at its poles, but these frozen deposits remain stable precisely because they never receive direct sunlight. So, Mercury's tail isn't formed through the sublimation of ice into gas. It's made of sodium. But why? To understand that, we need to take a look at its proximity to the Sun. At perihelion, Mercury comes as close as 47 million kilometers from the Sun, where it's exposed to solar radiation, up to 10 times more intense than what we receive on Earth. The solar wind is absolutely torrential. Imagine a constant stream of charged particles flying at 1.66 million kilometers per hour from the Sun straight at you. When those particles strike, they physically knock out other atoms on Mercury's surface in a process called sputtering. Picture a bunch of fridge magnets sitting on your fridge. They don't fall on their own because the fridge holds them in place. But then, say you throw a bouncy ball at the fridge. When it hits, the energy spreads out and shakes some of the magnets. If enough energy makes it to the weakest magnet, more energy than is what's keeping it stuck, it will pop off and fall down. That's exactly what's happening in a sputtering collision cascade. Ions from the solar wind shower Mercury, creating high-energy impacts that dislodge the weakest link atoms from the surface of the planet, just like the bouncy ball dislodged the weakest fridge magnet. It just so happens one of the most weakly bound elements on Mercury's surface is, you guessed it, sodium. Messenger data show that during periods of high solar wind activity, these solar wind particles rain down on Mercury's surface and result in a 50% rise in sodium group ions in the planet's atmosphere. This indicates that stronger solar wind activity enhances surface particle interactions, leading to a greater release of sodium into Mercury's atmosphere and hail. But there is more to the story. In addition to solar wind, Mercury is also tormented by micrometeoroids, and without an atmosphere to slow them down, even dust-sized particles strike the planet with tremendous force. These tiny space rocks vaporize surface materials on impact, releasing even more sodium atoms. We're essentially watching a process of space erosion, a planet that is slowly disintegrating over billions of years, right in our cosmic front yard. Some researchers have noticed enhancements in the tail that seem to correlate with times when Mercury is predicted to pass through denser streams of interplanetary dust, like debris from Comet Anchor. This would boost the contribution from micrometeoroid impact vaporization, temporarily increasing the amount of sodium injected into the exosphere and subsequently fed into the tail. But the shaping of the sodium tail isn't primarily due to the solar wind blowing it back, as is largely the case for a comet's ion tail. Instead, the dominant force sculpting Mercury's sodium tail is solar radiation pressure. This is a subtle but powerful effect. Photons, despite having no mass, carry momentum. When a sodium atom in Mercury's exosphere absorbs a photon of light, it gets a tiny push in the direction the photon was traveling away from the Sun. It then quickly remits a photon in a random direction, causing negligible recoil on average. However, it's immediately ready to absorb another photon coming from the Sun. This continuous process of absorbing solar photons and receiving tiny directed pushes effectively acts like a gentle but constant wind, pushing the sodium atoms away from the Sun. Imagine countless tiny solar sails, each one a sodium atom being persistently nudged by sunlight. This relentless pressure accelerates the atoms anti-sunward, overcoming Mercury's weak gravity and stretching them out into the vast elongated tail structure observed from Earth. Because radiation pressure acts directly away from the Sun, the tail reliably points in the anti-solar direction. But as I mentioned, despite being so big, it's not actually visible to the naked eye. So, how did scientists spot it? When sodium atoms absorb energy, they become excited, or their outermost electron jumps to a higher energy level. When this electron falls back to its ground state, it emits photons at a very specific wavelength, 589 nanometers. Light at this wavelength has a distinct color you've definitely seen before. It's the color of old streetlights. This process is happening constantly in Mercury's tail. However, the tail is hidden from the human eye and from standard telescopes. To reveal it, astronomers use specially designed filters called sodium Deline filters that isolate light at precisely 589 nanometers. These filters block all other wavelengths, allowing the faint glow of sodium to stand out against the black background of space. Mercury's sodium tail varies dramatically throughout its 80-day orbit around the Sun, which is highly elliptical. When Mercury reaches perihelion, the increased solar radiation dramatically intensifies the rate of sodium ejection from its surface. You might expect the tail to reach peak visibility at perihelion, since that's where the solar wind and radiation are strongest. However, it actually reaches peak 16 days later. Let me explain. Since Mercury's orbit is highly elliptical, its orbital speed also varies a lot from 39 kilometers per second when it's farther from the Sun to 59 kilometers per second when it's closer. Through repeated observations, scientists noticed that Mercury reaches its maximum radial velocity after slingshotting past the Sun, exactly 16 days after perihelion. In other words, that's when it's traveling away from the Sun at its top speed, creating optimal conditions for the sodium tail to extend and become more observable. But why would higher speed lead to a brighter tail? 2 words: Doppler shift. When we look at the spectrum of light from the Sun, we see dark lines, called Fraunhofer absorption lines, where certain wavelengths of light are being absorbed by elements in the Sun's atmosphere before the sunlight is emitted. The Sun's atmosphere contains sodium, just like Mercury's tail, which absorbs all the sodium-specific light before the light travels to Mercury. But the faster Mercury travels away from the Sun, the more the sunlight is Doppler shifted or stretched. This means the wavelength gets longer or redder. The entire sunlight spectrum is shifted, including the Fraunhofer lines. So the sodium-specific light is no longer blocked and is available for the tail to absorb and scatter. The result: the tail gets brighter, and we can see it from Earth. So, if astronomers wanted to spot Mercury's tail, they just need to look up on day 16 past perihelion, right? Well, it's not that simple. There are 3 other main factors at play to consider. Firstly, Mercury must be at a sufficient elongation from the Sun in Earth's sky so that it isn't caught in the glare. Secondly, it can't be behind the Sun from Earth's perspective. And finally, it must be at the perfect angle for Earth-based telescopes to view its anti-ward direction. This astronomical alignment only occurs during very specific periods, roughly every few years. And to think the scientists at McDonald Observatory caught it basically by coincidence. Talk about perfect timing. Some of the most spectacular images of Mercury's sodium tail have come from observatories utilizing coronagraphs, instruments that block the sun's direct light, allowing the faint glow of the tail to become visible even when Mercury is relatively close to the sun in our sky. Each successful observation represents a triumph of astronomical planning and precision. These rare glimpses show a dynamic that changes dramatically with Mercury's position relative to the sun, stretching, shortening, brightening, and dimming in a cosmic dance governed by orbital mechanics and atomic physics. But this story stretches beyond Mercury itself. It has provided an unexpected window into key processes occurring throughout our solar system and beyond. Firstly, it gives us a glimpse into planetary evolution. While the current rate of surface material loss is too small to significantly alter Mercury in human timescales over billions of years, this process could potentially affect its surface composition, gradually depleting sodium and other easily liberated elements. We could use this knowledge to infer what might have happened to older planets in other solar systems and understand their life cycle better. Secondly, and perhaps most excitingly, the discovery has profound implications for exoplanet research. Many star systems contain hot Jupiters, massive planets orbiting extremely close to their stars. If Mercury can generate a 2.5 million kilometer tail, these giants likely sport even more dramatic features, potentially shedding significant mass through similar mechanisms. The detection methods developed to study Mercury's tail are now being applied in the search for similar phenomena around distant worlds. By looking for the distinctive spectral signatures of elements being stripped from exoplanets, astronomers may gain new insights into their composition and environment. In fact, we have already detected similar sodium tails around our own moon, suggesting this phenomenon may be common around airless bodies exposed to solar wind. Mercury's sodium tail represents a perfect opportunity for studying planet-star interactions throughout the universe. By better understanding this phenomenon, we gain crucial insights into how stars shape and erode their planetary systems over billions of years. Bay Colombo mission has already completed 6 rapid flybys of Mercury. It's set to enter into orbit in December 2025, where it will spend at least one Earth a year studying Mercury's internal composition and its impressive exosphere. This will provide data on the sodium tail in unprecedented detail, promising new discoveries about this fascinating phenomenon. Mercury's elusive tail reminds us that, even after centuries of astronomical observation, fundamental discoveries about our closest cosmic neighbors are still being made. What other secrets might our cosmic neighborhood still be hiding? The universe never stops surprising us. All we need to do is keep looking.